On this question, we want to use the properties of logarithms and the logarithmic property of equality to solve the logarithmic equation. The equation that we have is natural log of 2 plus natural log of x equals natural log of 4 plus natural log of 4x minus 4. So in this example, we'd like to solve the logarithmic equation using the logarithm property of equality, and that's what I have written down here as the one-to-one property of logarithms. So in order to use this property, we need to have a log with a certain base on one side of the equation and a log with that same base on the other side of the equation. In this example, I can see that I have natural log ln on the left and natural log on the right. However, I don't have a single natural log on the left and on the right. So we're close to being able to use this property of equality, but we're not quite there yet. So before we use that property of equality, we need to use some of the other properties of logarithms in order to condense the expression down to a single logarithm. And the property that we're going to use is called the product rule for logarithms. And that product rule for logarithms follows this format. If you have log base b of m times n, you're able to expand that to become log base b of m plus log base b of n. So if you have a product inside of the log, you're able to write that as the sum of two logs. Now we're actually going to use that property in reverse to condense. So if we think of it that way, we have the sum of two logs with the same base, and we're going to be able to condense it to a single log by the product, multiplying those two expressions together. So that's what we have on the left-hand side here. We have the sum of two logs with the same base. These are base e, and we're going to be able to condense them. We have the same thing on the right-hand side. We have addition of two logs with the same base, and we're going to be able to condense them. So let's start by applying that product rule for logarithms. So I'll rewrite the question, natural log of 2 plus natural log of x equals natural log of 4 plus natural log of 4x minus 4. Just by the way, in case you were wondering why I wrote an e on here, natural log has base e. So we're going to use that product rule for logarithms and condense to a single log with multiplication. It becomes multiplication because we have the sum of two logs with the same base, so that's 2 times x. The same thing happens on the other side of the equation. We're going to condense with multiplication because we have addition of two logs with the same base. So this becomes 4 times 4x minus 4. So writing that a little bit more simply, that's natural log of 2x equals natural log of 16x minus 16. Now is when we're going to use this property of equality. We have a log with the same base on both sides of the equation, and with this property we can say that what's inside the log on the left will equal what's inside the log on the right. That would give 2x equals 16x minus 16. So now we have an equation with no logs in it, and we'll be able to solve this equation. We want to get all of the variables onto the same side, so I'll subtract 16x on both sides. That gives negative 14x equals negative 16. And then we'll divide both sides by negative 14. and that gives us x on the left, and on the right we're going to reduce that fraction. These are both even numbers. 2 goes into 16 8 times, 2 goes into 14 7 times, and a negative divided by a negative is a positive. We have one final thing that we need to do. The log is a function that has a restricted domain. We are only able to define log of a positive value. Log of a negative value is undefined. So whenever we solve a log equation, we always have to check to make sure that the answer we get is in the domain of the logs that we have in our original equation. So we're going to check to make sure that x equals 8/7 is in the domain of our expression. So I'm going to use this original equation to check that. We have natural log of 2 plus natural log of 8/7 equals natural log of 4 plus natural log of 4 times 8/7 minus 4. So what I'm checking is I'm making sure that the places I plugged in for variables will have a positive inside of that logarithm, which it does here and here and here. I have a little bit more work to do to check to see if it's true there as well. So that would be 32/7 minus 4, and 32/7 goes into 32. Let's see how many times. 4 and 4/7, and 4 and 4/7 minus 4 will be a positive, so it also is in the domain of that expression as well. So that means that we're going to be able to keep that solution of x equals 8/7. On this question, we want to find the domain of the logarithmic function f of x equals log of 2x plus 10. Now, in order for us to know how to find the domain of a logarithmic function, we have to know a little bit about logarithmic functions. So a logarithmic function is of the form y equals log base b of g of x. So this g of x can be any expression, and it is equivalent to this exponential expression. Logs and exponents are inverse operations of each other, so there's an equivalence between these two, and this is that equivalence. So you'll notice that the base of the log is the same as the base of the exponential. The log equals y, and y is in the exponent. So a logarithmic expression is really an exponent. And then this exponential expression equals g of x, and that is what we have inside the logarithm, the expression we have inside the logarithm. Now, some other information that is important is that we have some restrictions on the base. The base is only allowed to be a number that is greater than 0, and the base is not equal to 1. And we have this restriction because we want for these functions to all behave similarly, and they only behave similarly when we make that restriction of having the base greater than 0 and not equal to 1. So we can identify that we have a logarithmic function when we have a variable inside of a logarithm. This last paragraph that you see over here is talking about how we can find the domain of a logarithm. The logarithm of a negative number is going to be undefined. We can talk about that in detail in a second. The logarithm of 0 is undefined. And we're interested in finding where the function is defined, and that is only for positive values. We would like the expression inside the logarithm to be positive. So in order to find the domain, we would create an inequality to solve. And that inequality is the expression inside the logarithm greater than 0. So that's how we guarantee that the expression inside the logarithm is positive. So if we're able to create this inequality and solve it, that will give us the domain. So for ours, the expression inside the logarithm is 2x plus 10. We create the inequality of 2x plus 10 is greater than 0, and we solve. So we're going to subtract 10 to get 2x is greater than negative 10. We're going to divide by 2 to get x is greater than negative 5. So if we think about that on our number line, we would mark negative 5 with an open circle because we don't want to include negative 5. If we included negative 5, that would cause a 0 inside the logarithm, and that is undefined. And we want the values that are greater than negative 5. And so that's negative 5 to infinity. So this will be our domain. So anytime you're looking for the domain of a logarithm, you're going to take the expression inside of the log, create that inequality where you set that expression greater than 0 and solve, and you will get the domain from that inequality. Now I want you to notice here that I've used a parenthesis on the negative 5. Parenthesis has the same meaning as that open circle. It means that that point, that negative 5, is not included in the domain. If we were to include it, we would use a bracket. But remember, we're not going to include it because it causes a 0 inside the log, and that is undefined for the log. So I said I'd come back and take a moment to talk about why the logarithm of a negative is undefined. So it goes back to being the fact that logarithms and exponentials are inverses of each other. So if we were to try to think of log, let's say log base 3 of 0, so I'm substituting a 0 into the log. When we work this out, this is something that's not going to make sense because it's something that's undefined. So I'm going to try to relate it back to its exponential form. Log base 3 of 0 is some power. If I write this as an exponential, that's 3 to a power equals 0. And when I do that, I'm following this relationship here. This is the definition of a logarithm. So when we think about this statement, 3 to a power equals 0, we come to realize that that can never happen. There is no power that I could come up with, no exponent that I can come up with that would give an answer of 0. And so we get this expression being undefined. The same thing happens when you try to do the log of a negative number. If you try to think about it, you're going to say, okay, this equals some p, which is a power. Rewrite it in its exponential form. You get 3 to a power equals negative 1. And you can see once again that this can never happen. You cannot take a positive number and raise it to a power, a real number power, and get a negative answer. And so once again, we get an expression that is undefined. So this idea of relating the exponents and the logarithms only works when the value inside the log is a positive value. Okay, so I kind of strayed for a minute from the details of the problem, but Just to make it focused, whenever you're trying to find the domain of a logarithm, you're going to take the expression inside the logarithm and create an inequality. That inequality is the expression inside the logarithm greater than 0. Then you solve that inequality. And then from that inequality, you can graph the number line and also write the interval notation for that domain. And we got -5 to infinity. Jimmy invests $19,000 in an account that pays 8.91% compounded quarterly. How long in years and months will it take for his investment to reach $24,000? So first thing I want to focus on is some wording in this problem that indicates the formula that we're going to use. The interest is compounded quarterly, which means that the interest is compounded periodically. So I have this formula for periodic compound interest, and the formula is A equals P times 1 plus R over N to the NT. And the values in this formula are as follows. The P stands for principal, or the initial investment. R stands for the annual interest rate. N is the number of compoundings in 1 year. What that means is how often the interest is added into the account. So the number of times interest is added in 1 year. T is time in years, and A is the accrued amount, the amount after some period of time. So what I want to do is read through the problem again, and as I read through it, try to identify the values of the variables that we use in this formula. So as we start reading, it says that Jimmy invests $19,000 into the account. This is going to represent his initial investment. And so we're going to let $19,000 be P. So P is the principal, the initial investment. In an account that pays 8.91% compounded quarterly, 8.91% will represent the interest rate, which is R. So that's 8.91%, and we don't write this as a percentage when we use it in the formula. We put it in its decimal form. So I'm going to move that decimal point 2 places to the left, and the decimal form of 8.91% is 0.0891. So going back to that percentage, 8.91% compounded quarterly. Quarterly tells me how often the interest is added into the account. So it will be quarterly, and that's also an indication of the value of N. So if we compound quarterly, interest will get added 4 times per year. So the value of N will be 4. How long is a question, and that's an indication that the variable time is our unknown value and the value that we are trying to figure out. So T is time, and we don't know the time, and hopefully once we get all the information, we'll be able to solve the equation for time. How long in years and months will it take for his investment to reach $24,000? So this is the amount of money that we would like to have in the account after a period of time, and that is our accrued amount. So the value of A will be $24,000. So as I look at my formula, I'm going to check off the values that I have. I have a value for A, the accrued amount, P, the principal, R, the interest rate, N, the number of compoundings per year, and N again. And the only value I don't know is the value of T time. And so because I know all of the variables except for what I'm looking for, I'll be able to create an equation and solve that equation for the missing value. So let's substitute the values in, and that would give the equation 24,000 equals 19,000 times 1. I'm going to write this again and give myself just a little bit more space. Okay, so we have 24,000 equals 19,000 times 1 plus 0.0891 over 4 to the 4 times t. So I have an equation which I'd like to solve, and I notice that my variable is in the exponent. So I'd like to use my strategies for solving exponential equations to solve this. Before I do that, I think it might be nice to simplify what we have in the parentheses, since all of those are numbers. So let me grab my calculator and we'll simplify that portion. Inside the parentheses, we have 1 plus 0.0891 over 4. So that gives 1.02275. So now I have the exponential equation 24,000 equals 19,000 times 1.02275 to the 4t. Now when you solve exponential equations, the first thing that you should do is isolate the exponential portion. We want that to be the only thing on one side of the equation. So I'm going to divide both sides by 19,000. That quickly, if we're able to cancel out these powers of 10, gives me 24 over 19 equals 1.222, oops, I left off a 0, 1.02275 to the 4t. Now I'll use the strategy of solving exponential equations, and there's two strategies that we typically use. We either convert to a logarithm or take the natural log of both sides. I'm going to take the natural log of both sides so that it will be easy for me to type into the calculator once we get to the end. I'm going to do natural log of 24 over 19 equals natural log of 1.02275 to the 4t. And now that I've introduced the logarithm, I can use a property of the logarithms called the power rule, and it allows me to move that power into the coefficient. So that gives natural log of 24 over 19 equals 4t, natural log of 1.02275. And now I'm going to isolate t by dividing both sides by 4 natural log of 1.02275. So now we have our answer for time. Natural log of 24 over 19 divided by 4 natural log of 1.02275 We're going to type this into the calculator, and before we do that, I just want to remind you that the question asks you to put this in years and months. When we put it in the calculator, it will be initially in only years, and we'll have to do a conversion to put it in months, years and months. So in the calculator, we have natural log of 24 over 19 divided by, and I need parentheses around my whole denominator, 4 times natural log of 1.022275. I'm going to close parenthesis for the log and close parenthesis for the denominator. So that's going to give me 2.651 and some more decimal places. I'm going to write 2.65 down. But because I'm going to do a little bit of converting here, I'm going to try to keep all of the decimals in the calculator here. So as I look at this, this is in years. And if I take the 2, that's going to be 2 years. And I'm going to take this portion to help me figure out how many months I have. So that's 0.65, which is more than half of a year. So we know it's going to be more than 6 months. But let me show you how in my calculator I'm going to figure this out. So first off, I'm going to subtract 2 from the answer because I'm not concerned about the years portion. I'm only concerned with the months. And in order to convert this in years to months, I have to know how many months are in a year. There are 12 months in a year. So I'm going to be able to multiply this value by 12. And that converts this to months. And since we have another decimal answer here, and it only wants it in years and months, I think I'm going to round up to 8 months. So I've got 7.8 months, which I'm going to round up to 8 months. We have 2 years and 8 months is how long it takes for $19,000 to grow to be $24,000. So after rereading the directions on this problem, I wanted to come back and modify our answer just a little bit. So if you recall, in the beginning of the problem, it's mentioned that our interest is compounded quarterly. And that's an indication of how often the interest is added into the account. So just to explain it in a little bit more detail, let's think about the first few months of the existence of our account. We make an initial investment of $19,000. So in the first month, we're going to have $19,000. In the second month, we have $19,000. And then in the third month, we're going to have our interest payment added. That's going to be $19,000 plus whatever that interest calculation is going to be. So when we consider our problem, we came up with an answer of 8 months, but that's a month where interest wouldn't be added. So if we write out the months of the year, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And because we're compounding quarterly, interest is going to be added in months 3, 6, 9, and 12. And so when we're trying to decide when the balance will reach $24,000, like in this problem, it can only occur on those months where interest is being added in. So we're going to round this 8 months up to 9 months so we can more align with the construction of this example. So it would take 2 years and 9 months for the balance of $19,000 to grow to $24,000. We want to classify the given function as a polynomial function, a rational function, or a root function, and then find its domain. Write the domain in interval notation. The function we're working with is g of x equals the 8th root of 9 minus x. So I don't know if that makes the classification of the function obvious, but we have the 8th root, and that's going to make this a root function. Now, more specifically, we want to pay attention to the index of the root, because the index classifies it even further, and we find the domain differently when we have an even index versus an odd index. So 8 is an even number, and so we have a root function with an even index. A root function is a function of this form, the nth root of some expression g of x, and we are doing an even root. And what we want to pay attention to is that when we take an even root of a negative number, that's going to result in a complex or imaginary number. Right now, we're only interested in real function values, and so we are not going to consider these imaginary or complex numbers. So that means that we need to restrict what is allowed inside of our radical or underneath the radical. We want only non-negative values, 0 or positive. So when we're trying to find the domain, we're going to create an inequality where the expression underneath the radical is greater than or equal to 0. And when we solve that inequality, it will lead us to the domain. So for our function, g of x equals the 8th root of 9 minus x. 9 minus x is the expression underneath the radical. And we're going to create that inequality. 9 minus x is greater than or equal to 0, and solve. So we're going to subtract 9. That gives negative x is greater than or equal to negative 9. Divide by negative 1 on both sides. We're dividing by a negative, which means we need to reverse the inequality symbol. And that gives x is less than or equal to 9. On the number line, we would mark 9 with a closed circle, a filled-in circle, because we're going to include 9 in this set, and we want to shade all the values that are less than 9. So if we want to write that in our interval notation, that will be negative infinity to 9 with a bracket on the 9. So that bracket has the same meaning as the filled-in circle. So we have negative infinity to 9, including 9 as the domain of this root function with an even index. The price P and the quantity X sold of a small flat-screen television set obeys the demand equation below. So that's referring to this equation here as the demand equation. P equals negative 0.11x plus 220. How much should be charged for the television set if there are 60 television sets in stock? What quantity X will maximize the revenue, and what is the maximum revenue? What price should be charged in order to maximize the revenue? So I want to focus on what the variables stand for a moment. The price P, so P represents the price, and the quantity X, so this quantity is the number, how many flat screen television sets we have. So in part A, it asks how much should be charged, that's the price, for the television set if there are 60 television sets in stock. So 60 is the quantity of television sets, that's the value of X, and we're looking for the price P, how much should be charged. So in part A, we're going to use the demand equation that was given to us, P equals negative 0.11x plus 220, and we're going to let the value of X be 60, and that will tell us the price that we should charge. So negative 0.11 times 60 plus 220. I'm going to bring up my calculator. Let me clear out these keys so that you can see which buttons I'm pushing. We're going to do negative 0.11 times 60 plus 220, and we should charge $213.40 if we have 60 television sets in stock. Then moving on to part B, it says what quantity will maximize the revenue? What is the maximum revenue? So this is introducing something that hasn't been shown before, the revenue. And in order for us to answer what quantity will maximize revenue, we need to have an equation that represents revenue. There is a formula, a business formula that will give us that equation for revenue, and that formula is R for revenue equals X times P, and it's using the X and the P that we saw earlier, the price and the quantity. So we're going to use the demand equation that was given to us and substitute that in for P, the price, and that will give us a revenue equation. So we have X times negative 0.11x plus 220, and that's negative 0.11x squared plus 220x. So now we have an equation that represents revenue. So our equation represents revenue, and now we want to answer this question. What quantity X will maximize the revenue? So we have some theory to look at before we're able to answer this question. So here is the thought process that goes into this. Our revenue equation or function is a quadratic equation. I know it to be a quadratic equation because of the squared. The graph of a quadratic is a parabola. And if I know the coefficient on the squared term, what we usually call the leading coefficient, that will tell me whether my parabola is facing up or down. So this is A, which is negative 0.11, which is a negative leading coefficient, and that tells me that my parabola will be a down-facing parabola. Now this is significant because we're looking for the maximum revenue, and the maximum here will occur at this little peak, which we call the vertex. So that maximum value is the vertex. So we are going to use the fact that this equation is a quadratic, a down-facing parabola, to find the maximum value, and we do that by finding the vertex. We do have a formula for the vertex. The vertex is usually written as an ordered pair, HK, and we can find the value of the vertex with the formula negative b over 2a. So for our revenue function, we've already stated the value of a is negative 0.11, and the value of b will be this coefficient on the x term, 220. So we'll substitute those values into the formula. That's negative 220 divided by 2 times negative 0.11. I'll use my calculator to work that out. That's negative 220 divided by, and I need parentheses around the denominator, that's 2 times negative 0.11, and we get 1,000. So this is going to answer the first question on part B. What quantity will maximize the revenue? So 1,000 television sets will maximize the revenue, and we also want to know what is that revenue. So to answer that question, we want to substitute 1,000 into the revenue function. That's negative 0.11 times 1,000 squared plus 220 times 1,000. And I'll use the calculator to help me work this out. So we have negative 0.11 times 1,000 squared plus 220 times 1,000. So we get the maximum revenue to be $110,000. We have one more part to go, and we want to do this part right here. What price should be charged in order to maximize the revenue? Now we have this demand equation, which will give us the price that we should charge. So we're going to substitute x equals 1,000 into that demand equation. Negative 0.11 times 1,000 plus 220. Once again, I'll use my calculator to help me. We have negative 0.11, that's 11 hundredths, times 1,000 plus 220. And that gives $110. So we should charge $110 in order to maximize the revenue. For this question, we want to use the properties of logarithms to rewrite the given expression as a single logarithm. Wherever possible, evaluate the logarithmic expressions. The logarithmic expression we're given is natural log of x minus 1 squared plus natural log of 5x squared. So one thing to take note of is that these individual logs both have natural log, which is base e. We're only allowed to write logarithms as a single logarithm when they have the same base. So these have the same base, we are able to write them as a single logarithm. Now we notice that the two logs are being added together, and when they're added together, we're going to be able to use a property called the product rule. So when you have logs with the same base being added, we will make them a single logarithm, condensing them with multiplication. So we can use that product rule on this example to get natural log of x minus 1 squared times 5x squared. That's natural log of 5x squared times x minus 1 squared. And I would probably leave it in this format. I think it looks the cleanest. But if you would like, you can also multiply out this squared, x minus 1 times x minus 1, and then use the distributive property, distributing the 5x squared. So let me show you what that looks like. We would have the natural log of 5x squared and x minus 1 times x minus 1. It's the natural log of 5x squared times x squared minus x minus x plus 1. So this is the natural log of 5x squared times x squared minus 2x plus 1, which is the natural log of 5x to the 4th minus 10x cubed plus 5x squared. And there's a secondary statement on this question that says, whenever possible, evaluate the logarithmic expression. In this example, we have no further simplification that we could do. As I said before, I would argue that this original expression looks cleaner, and so I would probably leave it in that format. Natural log of 5x squared times x minus 1 squared. On this question, we want to find f plus g, f minus g, f times g, and f divided by g. And we also want to determine the domain for each function. So I'm going to start by finding the domain of each individual function we're given. F of x is square root of x, and g of x is x minus 15. F of x is a square root function, and we know that square root of a negative will produce imaginary numbers. Square root of 0 and square root of a positive will give us real numbers. So we can find the domain of this by setting the expression underneath the radical greater than or equal to 0 and solving. In this example, the expression is x, and so there's nothing really to solve. The domain will be all numbers that are greater than or equal to 0. And so that is a domain. I'm going to say domain of f is going from 0 to infinity. The function g of x is equal to x minus 15, and that is a linear equation, which is in the larger category of polynomial functions. And all polynomial functions have a domain of all real numbers. So we know that the domain of g is all real numbers or negative infinity to infinity. So let's take the time to find f plus g. F plus g of x is the name of our function, but it also tells us how we can construct the function. We want to take a function called f and add it to a function called g. And f of x is square root of x, and g of x is x minus 15. None of these are like terms, and so we're going to leave this one just like that. Now, when we take two functions and combine it like this, we have to consider the new domain of this function. This portion is only allowed to be greater than or equal to 0, and this portion can be anything. So because this one piece is restricted, the whole function is restricted. So the domain of f plus g will be from 0 to infinity because one piece of it is restricted. Then let's find f minus g. So once again, f minus g is the name of the function, but it is also telling us how to construct it. We want to take the function f of x and subtract g of x. That's square root x minus the whole function x minus 15. So we need to make sure to distribute that minus. So that's square root x minus x plus 15. And we want to find the domain of this function. And once again, this piece is restricted, this piece is not. But because one piece of it's restricted, we need to use that restriction for the new function. So the domain of f minus g is from 0 to infinity because of that restricted square root. So let's find f times g. F times g is the name and also how to construct it. We're going to do f of x times g of x. That's square root of x times x minus 15. We could write this, we could do the distributive property to simplify, and that would be x square root x minus 15 square root x. This radical is restricted. The x and the 15 are not, but since one piece is restricted, the function is restricted. So the domain of f times g will be from 0 to infinity. So we've got one more to go. That's f over g of x. We're going to construct that by doing f of x divided by g of x. And f of x is square root x, and g of x is x minus 15. There's not really much we can do to simplify this expression, so we're going to leave it. But we do want to consider the domain. This piece in the numerator is restricted because of the radical. It has to be greater than or equal to 0. And this piece in the bottom, because it's in the denominator, is also restricted. It cannot equal 0. So in the denominator, I need to figure out what value is restricted. X minus 15 equals 0. We're going to add 15 to both sides and get x equals 15 as our restricted value. So I'm going to take this one a little bit slower because we have an extra restriction. So let's think about that on the number line. Because of the radical in the numerator, we know that x is allowed to be values greater than or equal to 0. It is not allowed to be these negative values because square root of a negative would give you imaginary numbers. And then we have this second restricted value of 15, and that is over here somewhere. So we need to exclude that value of 15. And because we had to exclude 15, that gives us two separate shaded regions, and we're going to write down those intervals for our domain. So this interval here begins at 0 and goes to 15, and 0 can be included, so we're going to put a bracket, but 15 cannot. So we'll put a parenthesis. And this interval here begins at 15 and goes to infinity. And so we have the domain of f over g can be from 0 to 15, including 0, and 15 to infinity, not including 15. Thank you for checking out my videos. Have a great day.